I have 3 light bulbs here and a generator. The generator works by converting the kinetic energy of my moving hand into electricity, which the bulbs then convert into heat and light. But as you probably noticed, although I'm turning and putting in energy, and the generator is in fact making electricity, the bulbs aren't doing anything. And the reason for this is important. It has to do with how fast I'm turning that knob. Watch what happens as I speed up. Now I think you're seeing a little bit of light in each of the bulbs. Not much, but a little as I go faster. And as I go faster and faster and faster, you actually start seeing quite a bit of light. Ooh. So the speed at which I'm supplying this energy is important. It's not good enough just to give energy. I have to give it fast enough. We call the speed of energy power, and it's measured in the unit of watt. And what we're going to see as we look at different devices is that they have a requirement for how fast they need energy. Your toaster, for example, might be a 1200 watt toaster. That means every second it needs 1200 joules of energy in order to supply the heat needed to toast the bread. You could take that energy and spread that out over a longer time by leaving your bread in the sun all day. It would get the same amount of energy, but it wouldn't get it fast enough and it wouldn't be very tasty. The same is going to be true for almost every electric device. So the watts, how quickly it uses energy, are something very important that we'll have to pay attention to. What I'd like you to remember power as being the speed of energy. So what do I mean by that? If you think back to when we were learning about speed, we have a distance time graph, and we called the slope of that graph the velocity. So we took change in distance over change in time at a couple different points, and how steep that slope was represented how fast you were going. In this case, this would be something moving faster. That would be something that slowed down. If you understand that, you understand the relationship between energy and power. If we have an energy versus time graph, where you have a steep slope, that's when energy is being used faster. A shallow slope, that's where energy is being used slower. So power is just the change in energy over the change in time. It would be much easier to remember it as the speed of energy if we just called it the joules per second, just like we called the speed of distance meters per second. But unfortunately, we have a tendency in physics to name units after people. So the joule per second is often called a watt. So it's hard to train yourself to think this, but whenever you see joules per second, I need you to think that we're talking about a speed, how fast we're using energy. And that's measured in watts. So here's a graph of energy versus time over the course of an afternoon. And I want you to look at it again, just as we did with a distance time graph. The speed of energy use, which is the power, is how steep this graph is. So you could see that peak power occurs when we're at the steepest, which is in the afternoon. This is the hottest part of the day, so air conditioners are running. You also have people getting home, starting up appliances at home, although the business world and schools and stuff are still pretty active. And if you're the electric company, you have enough power available. You have to be able to generate energy fast enough to meet the demand at this point in time. You have to make energy fast enough for people to use energy this quickly. So in other parts of the day, you are generating energy more slowly. That means you have to turn electric generators off. So power companies try various techniques to try to encourage usage at these other times to make them steeper, because they have to build power plants to correspond to their steepest part of the day. So power is a very important concept. We can combine a lot of the ideas we've learned about energy and power together to generate some interesting new equations. So if power is the change in energy over the change in time, and the energy change here is coming from work that's being done, power is the change in work over the change in time? Well, if we sub in the work equation, work is F dot D, and we have a constant force, we're left with power equals F times delta D divided by delta T. We know delta D divided by delta T, distance divided by time, that's a velocity. And that gives us essentially power equals the force times the velocity. So if you know how fast somebody's going, and you know about the force that's being applied to them, you understand a little bit about the power. One important thing worth noting here, the work you do is not exactly force times distance if the force and the distance you're going are not in the same direction. So this force is at an angle, and only part of it, the blue part here, is in the same direction as distance. This is a desk I'm pushing, and since I'm not pushing it off the ground at all, this part of my force is useless. So we only want this one, and we see that that part is actually F cos theta. So the work in that case was really FD cosine theta. So that would make our power equation FV cosine theta. I only bring up this point about only part of the force mattering because what we're going to do next is a lab where students are going to run upstairs. And they're going to be moving a distance up the stairs. But the only distance that's really going to matter is straight up because they're working against the force of gravity. And the force and the distance need to be in the same direction. So in this lab, you're going to run up a flight of stairs. And you basically are going to have a meter stick and a stopwatch and a bathroom scale. And the question is, how much power are you exerting as you do this? So the distance in question you're going is the entire height of the staircase. As we just said, not along the staircase because gravity is an up-down force, so we only care about the up-down distance. So to figure out how much power you're exerting, the equation is pretty simple. Power is delta E over delta T. In this case, it's potential energy it's changing. So we plug in the equation for potential energy and how long it takes you to get up the stairs. And that ought to get the power you exert. So you can kind of guess from this equation what's going to matter. Having more mass is going to require more power to get up the stairs. Going higher is going to require more power. Since delta T is on the bottom, the more delta T you have, the more time it takes you, the less power it's going to be. So we're going to run up the staircase, we're going to time ourselves, we're going to weigh ourselves, and learn about the height of the staircase. And that's going to get us our power that we exert. So this is the calculation for a run I did at Southmore High School. In order to calculate it, you need your mass in kilograms, which you can get by multiplying your weight in pounds by 1 over 2.2, or dividing by 2.2. You then need the height of the staircase. So at Southmore, the main staircase, each riser was 17 centimeters, 0.17 meters, and there were 15 of them. At other schools, it will be different, of course. So that's my H. The energy we're talking about is potential energy, so I've got my change in potential energy here. And I started at height 0, and I ended up at height 2.55 meters. So for this particular run, I exerted about 1,184 watts, which is about a standard toaster. That's how fast it turns energy into heat. So that's basically the calculation. Here's another example. You just need the change in height somebody has, you need their mass, and you need the time it takes them. So your homework for the weekend is going to be to carry out this calculation for yourself and to write a lab conclusion about this lab and the power that you exert running upstairs.